So here we begin with the June 2013 multiple choice review of the chemistry Regents. All right, so here we're going with number 1. And as I zoom this up, I want to make sure that you understand that my kind of review here is going to be one which I'm going to assume that you know nothing about the problem. If you're looking for a review for just quick, easy hitters, probably not my type of review. So number 1 deals with atomic structure. This test, and multiple choice wise, they go in order for the most part in part 1. In any case, number 1, according to the wave mechanical model of the atom, an orbital is a region of the most probable location of, well, that would be the electron. Okay, so the electron is the answer, choice 3. Now, the wave mechanical model of the atom is the current model. Okay, that's the current model. Sometimes you hear wave mechanics. It deals with, number 1, electrons acting as waves. It deals with probability. Now you say, why am I even dealing with the rest of this? Well, because the deal here is that you could see this question another way. So we deal with electrons acting as waves. We use probabilities to determine where their location is because we can't look at single events in wave mechanics or the quantum mechanical model. All right, so alpha particle, gamma ray, and a proton might be something that may confuse you. So you probably do not need it, but you should know, just in case you get a question that's very similar, that there is something called table O to the rescue if you don't know what these things are. But in any case, what you should know is that the current model, number 1, is sometimes called the electron cloud model. So you'll hear it as the electron cloud model, which is the wave mechanical model or quantum mechanics. They have those 3 synonyms. 2, we're dealing with, as I just said, probabilities. And 3, you'll hear the word orbital. Now, the word orbital comes from Bohr's model, not so much because Bohr's model was a model where you had protons in the middle and electrons traveling around in orbits, but to give Bohr a lot of respect for his model that was based on energy levels, quanta. He was the first to talk about electrons existing in exact energy levels to go from one to the other. Because he was the first to introduce quanta from Einstein in these exact energy levels for electrons, they used the word orbit to give him a lot of respect. Now, it's not an orbital, or it's not an orbit in terms of electrons traveling in circle paths. The orbital part is to show they exist in these regions of space. If you went a little further in your class, although not part of the regions, an s orbital is spherical. Now, what does that mean? It goes in a circular shape? No, these electrons exist somewhere in this region of space that's circular with, again, high probability, and that's why they call it an electron cloud. If you went any further, you looked at one of the p orbitals, you'll see that they take on a dumbbell shape, okay? And electrons exist with high probability in these regions, okay? And these, of course, would be nodes here. So again, I'm giving you a little more than you probably need for the question, but you could see the question other ways. Just because you got the question right, the way it was presented may not be the way you'll see it and where they're looking at it in this June Regents or any Regents you're going to take. So clearly number 1 is 3. Number 2, still an atomic structure, which particles have the same mass? Well, you should know that a proton and a neutron have the same mass. They're given 1 atomic mass unit, 1 AMU. Now, if you did not know that, 2 reasons why you should. Case in point, if I have helium, you should know this is the atomic mass. Oops, that's a doohickey. Sorry, sometimes that'll happen. You should know that helium. Whoops. You should know that helium has an atomic mass of 4. Okay, and atomic number, of course, this number is what identifies the element. That's how many protons. And of course, so this is a 2 proton number, and we know this has a mass of 4, but this is what? Well, this is some number of protons and neutrons. So you probably already know, in order to get neutrons, what do? You subtract. And you get what? 4 minus 2, you get 2 neutrons. And you get of course, the atomic number is 2 protons, and that's what equals the atomic mass. But if you didn't remember that the mass number is the what? The protons and the neutrons, and this is the protons, and subtracting them gives you the neutrons. Table O, as I mentioned in Table 2, is your friend here. So Table O lists all the particles by name, gives them the symbols. Some of these symbols are represented in Table N for radioisotopes, especially if they come from unstable nuclei from nuclear chemistry. But that's not part of the atomic structure unit as per se the Regents goes in terms of how they ask questions. They leave those questions the last. So beta particle, gamma radiation, these are particles and or energy emitted from an unstable nucleus, radioisotopes. So these primarily are dealt with, identified with half-lives and which particle or which isotope gives them off in Table N. But what we can use from Table O is the top number is the mass number, number. If you look at a neutron as one atomic mass unit, look at a proton, which they use a hydrogen here because it has basically one proton and no electrons if it's an H+, but in any case, it has a mass of 1. And so a neutron and a proton have the same mass. Notice an electron, now you may say, Mr. Grashka, electron's not emitted here. Well, beta particle forever is considered to be a high-speed electron emitted from the nucleus. They emit this now. So this is a 0 for an electron. Now the electron doesn't have 0 mass, but it's considered to have no mass compared to these big particles. You should remember that a beta particle electron is 2,000 times smaller. You will see those questions. So number 2, clearly number 2 is a neutron and a proton. Number 4. Okay, number 3. During a flame test, lithium salt produced a characteristic red flame. This red color is produced when electrons in excited atoms do what? Okay, well this is back to what Bohr first described with his quantized level of electrons in his circular orbits. Now his circular orbits are not true today, but we can use those circular orbits to come up with a way to describe energy changes. So in any case, here's a positive nucleus, and here are my energy levels. And what we should know is that electrons that can exist or do exist closer to the nucleus, if you remember, are going to have lower energy. Now, some people say they lose a lot to get to this position, but for the Regents level, we're going to say they have lower energy. And you can think the reason why they have lower energy because of their proximity to the positive nucleus. The positive nucleus is controlling them, so therefore there's a large amount of attraction there. This electrostatic attraction means this electron isn't free to do very much. Now, if you were to gain some energy, like in a flame test, you add some energy from a candle or Bunsen burner, electron can leap to higher energy levels. So now they can exist farther away, and we call that an excited state because they have high energy. And they must have high energy to overcome this attractive pulling force. And they get this high energy from energy that it's being absorbed. So in any case, in a flame test, you're adding heat, energy is absorbed, electrons that are close to the nucleus can pull away because they're gaining high energy, and they exist in this excited high energy state. But that's only half the story. The other half of the story is because of this high energy state and being unstable with high energy, they eventually leap back, sometime in one big leap or in smaller leaps. And these leaps mean that they're going to lose energy as they get closer to the nucleus. So therefore, energy is going to have to be released as they jump back. So as energy is emitted, they're jumping back to orbitals or orbits closer to the nucleus. So the red color is produced when electrons in excited lithium atoms move to or return to lower energy states within the atoms. When you if you knew nothing about this, in order to emit energy and light, and the red flame has a characteristic wavelength which is associated with a frequency and of course energy, to go to a lower energy state you have to emit, and you should know emitting energy in the form of light or electromagnetic radiation Sometimes they'll use the word photon or spectra in these types of problems. These are all synonyms. You can see it different ways. Means that you're returning to lower energy states closer to the nucleus. Choice 3. 3 is 3. Number 4. Compared to the energy and charge of the electrons in the first shell of a beryllium atom, the electrons in the second shell of this atom have. Well, okay, let's go look what beryllium is in terms of its electron configuration. Okay, so this beryllium, I'm looking at your reference table given to you for the Regents, the one you've been working with probably all year, and its configuration is 2-2. Now this 2-2 is basically an abbreviation of something you might have learned, 1s2, 2s2, and you don't have to know this, but you should know there's 2 electrons in the first energy level, and there's 2 energy levels in the second principal energy level. Now, we will use the phrase shells. So this is the first energy shell. Think of the electron configuration as the nucleus in front, and this is the first shell. 2 electrons exist in the first shell, and 2 electrons are existing in the second. We know that the first shell holds a maximum of 2. That's why you see these 2's written here. You fill 2, you have to what? Once you have 2 electrons in this energy shell, you start filling the second. Now the second one, as you can see, holds a maximum of 8. How do I know? If we look in the periodic table and move on, 8 is the maximum number. If I'm in the 4th principal energy level, that must mean that my second energy level must be filled. Okay, so 2-2. So in any case, comparing the energy and charge electrons in the first shell, the electrons in the second shell have, well, knowing that we have 2 electrons in the first shell, here's my nucleus, and knowing that that first shell is filled, we call this filled shell a kernel, or it's in the kernel. The kernel are very stable. Anytime you fill an energy level, electrons are part of the core, and sometimes we'll call this the core electrons in other courses, or the kernel. It's what basically the Regents like to use. These kernel electrons are very, very stable, held very closely to the nucleus, very hard to rip off. And we know that filling energy levels is what essentially noble gases are able to do, or at least they are already at that state. So that's why they are unreactive, because they already have basically kernel electrons. They don't have valence electrons for the most part. I know there's a stretch beyond, okay, atomic number 3, but we'll stay with that definition that noble gases have basically they basically have core electrons. They don't have valence because they filled their energy level, at least they filled all their available orbitals. Any case, electrons in the second shell, you should know, are valence electrons. These electrons are not filled. As I spoke in terms of the periodic table, there's a maximum of 8 that fills the second shell. A maximum of 2 fills the first shell. So because 8 fills the second shell is not filled, therefore it's valence. And valence electrons, okay, are very unstable. And they're unstable because, well, they're available for bonding. They haven't filled their energy level. So therefore, electrons in the second have more energy. More energy means what? Unstable. It's very important you got that concept down. Being unstable means you have high energy. Now, why are they unstable, high energy? Because all they got to do is gain or lose electrons to be what? Like a noble gas. All right, and of course, electrons all have the same charge. If you go to table O, that beta particle I showed you is 0e -1. All electrons have a -1 charge. So 3 is the best answer. Valence electrons have more energy because they're unstable, they're not filled, and they barely want to gain and lose to do that. Now, as I overteach every question, look at neon as 2-8 here. It's got what? It's got filled first and second. Neon is totally unreactive because of that. Fluorine is 2-7. It needs what? 1 more electron. That's why it likes to become -1. That's why fluorine starts out with 7, and if it's hooked up with something like sodium, who, by the way, is 2-8-1, Okay, this fluorine, all he needs is one electron to become -1 and as stable as neon because it fills and becomes 2-7 becomes 2-8. Sodium, as we go across the periodic table, as I just said, is 2-8-1. So by losing one, it becomes +1, and by losing one, it also becomes 2-8. So the driving force of bonding is that these electrons that are not in filled energy levels are unstable because they're gonna do something. They're gonna get their energy levels filled, okay, to become low energy and unreactive. Okay, so last question was clearly number 4 was that electrons that are valence, which means they are the outermost electrons in unfilled energy levels. In the case of beryllium, of course, 2-2, this could use 6 more, okay? Beryllium likes to lose 2 to become like just 2, which is helium. Any case, the answer here is they have more energy and are the same charge as other electrons that are close to the nucleus. So 4 is definitely 3. Number 5. Which quantity can vary among atoms of the same element? So if we have the same element, we know one thing. For instance, carbon. Carbon has atomic number 6. This is the atomic number. Now, why is it the atomic number? Because it identifies the element. Only carbon has 6 protons. That's what keeps or makes carbon unique. Nothing else, my friends. Carbon can have different number of protons. I'm sorry, different number of neutrons, not protons. That's counterintuitive what I just said. So 6 protons is what identifies carbon. And we know that if we have carbon, we can have carbon 12 and carbon 14. Now, most people identify the element with their mass number because you don't need it. It's implied once you write what? C, that we have the 6 below here. It's not cool to write it in. So any number associated with the element tells you which isotope. And isotopes are the same element, same atomic number, therefore the same symbol, but what? Different number of neutrons. So if we go 12 minus 6, because we know that the mass number is the protons and neutrons, we have 6 neutrons here, and 14 minus 6, we have 8 neutrons. So back to the question, which quantity can vary? Well, I'm going to cross out protons. Protons can't vary. If you're the same element and you're the same atom, the number of protons. Number of electrons I'm also going to cross out, because if you're an atom, and I say this to my class, if you're an atom, okay, you are a neutral entity. Now, of course, you have positives that come from protons, and you have negatives that come from electrons. So as you know, this top number, or this bottom number here, is the proton number. However, it is also the number of electrons, because negative 6 and a positive 6 equals 0. And all atoms, once you hear that word, must be neutral. So the number of electrons are crossed off because they're not going to vary if they're atoms, if they're neutral. Atoms mean neutral. The atomic number, of course, is the same as the number of protons, so that crosses off. What can vary is the mass number, as I just showed you, because isotopes, iso means same, same what? In this case, same carbon symbol, same number of protons, but different number of what? Neutrons. So isotopes are the same element, different number of neutrons, a heavier or lighter form of the same element. So the mass number can vary. And that's why when you say, hey, I got carbon, you'll see carbon 14, you'll see carbon 12, you'll see helium 3. That number tells me which isotope of the element I'm talking about. But they're not telling me which atom, because I know clearly that once you give me this symbol, I'm stuck with a proton number that's only 1 for that element. Okay? I know I overtaught that again, but 5 is 1. Number 6, which substances? You should know substances are homogeneous compounds made up of just elements, which you now know are just the same number of protons, or compounds, which are made up of two or more different elements bonded in a distinct ratio, which we call a molecule. So we're looking for substances. Substances have atoms of the same element, but different molecular structures. Well, this is kind of silly because choice 1 has two different elements. So does choice 3, and so does choice 4, so it can only be choice 2. I'm not really sure what they were after in this question. But just to expand on this, as you know, the Lewis dot diagram for oxygen, oxygen has 6 valence electrons, and of course another oxygen would have 6, and you'd have to put a pair together to make a double bond. And the reason that we do this is to show that this oxygen is sharing 8, and this one is also sharing the 8 called the octet that we're kind of bound by in this course. So sometimes we'll see the O double bonded to an O, should show the lone pairs. Now ozone is something you would study at a higher level, but ozone, okay, has a resonance structure. We have a 1, 2, 3, 4, let's say 5, 6, okay, and this one oxygen would supply the double bond like the other one, and the other one would not. It'd have a single bond. And these would have different molecular structure. For those that study and learn about VSEPR theory, this lone pair would bend this pair downward into a bent shape. I'm not going to get into the resonance structure, not part of the course, but this, because different structure, different molecular properties. I know they're not talking about this here, but I've seen this question many ways where they say, which of the following are made up of the same element but have different chemical and physical properties? And you'd pick these guys, which by the way are called allotropes. Allotropes is another word that could pop up. They're the same element but different structure. And as I say in my course all the time, structure is king. You know, if there's a different structure, they have a different set of properties. So these are both made of molecular oxygen, yet they have different structures. Therefore, they have far, far different properties. Okay, so many ways to see this question. These are examples of allotropes. So choice 2 is the best answer. Number 7, an atom that has 13 protons and 15 neutrons is an isotope of the element. Right away, I see isotope. I know that's the same element, different number of neutrons. So the key to me here is 13 protons. Who has 13 protons? Let's go find that element. That'll be my answer. Because if I'm an isotope of something of 13 protons, then I have to be that element. Okay, let's go get it. Let's go to the periodic table. And there it is, aluminum, atomic number 13. Now, just for fun, this number 26.98 rounds off to 27. You've been probably taught to round that number off, and for good reason, because that is the most abundant isotope that exists in nature. If you're doing the weighted mass problem, you'll know that most isotopes, 1 or 2 of them are existing. Well, most atoms have over 20 isotopes, different forms, which means different number of neutrons. But the 1 or 2 of them have the highest abundance, and usually it works that and it's a good practice to do this, that one of the isotopes is in a larger abundance. So 26.9 means that the isotopes that exist in nature with the greatest percentage, or the greatest amount that we find in nature, is aluminum 27. So if you do 27 minus 13 for some more fun, you get 7 minus 3 is 4. You get aluminum with 14 neutrons. So the isotope of aluminum that's most common is aluminum 14. I'm sorry, aluminum with 14 neutrons. Aluminum 27 is what we would say there. So aluminum 27, oops, as we said, has 14 neutrons. That's the most abundant. Man, they're talking about another isotope that has what? 13 protons, which makes this aluminum, okay? And of course, 15 neutrons is a different isotope. Again, I'm over teaching, but I just want to show you all different ways they could be talking about this problem. Aluminum is the answer. 7 is 3. Number 8. Which elements have the most similar chemical properties? Now, if you've got similar chemical properties, this screams to me valence electrons, because Mendeleev, the Russian who put the periodic table together, although there was many people who did that, he got the credit for it because of, I think, publishing first. But in any case, he didn't know anything about electrons or protons. All he knew was about properties, and he saw properties repeating themselves. And when he was putting them in order of mass, of course, the atomic periodic table, of course, is now numbered in proton number, atomic mass. He realized that once he got to a certain row, the properties started repeating themselves, so he put the elements underneath each other. So he saw way back when, way before we put new protons, electrons, and a lot of different things, that elements that had similar chemical properties, okay, were in his same row or column. So in any case, we know now it's valence electrons. So I'm looking for atoms that are in the same group, and we know a group on our periodic table, first started by Dmitri Mendeleev, what basically is done by valence electrons. So let's go find who they are. So one of our choices is magnesium, strontium, and barium. And all of these guys are in group 2. And you notice they all become what? Positive 2. They all lose 2 electrons. They lose their 2 valence to, guess what? Have a filled octet, or they have a filled energy level. And group 2 is right here. And group 2, okay, group 2 tells us that there are 2 valence electrons. And it's one quick way to get valence electrons. Group 1 has 1 valence. These generally have 3, 4, 5, 6, 7. We can stop here, and there's some games that are being played between the S and the D, and there's overlapping of energy levels here, but you can use that. And you can also go to the other side of the periodic table, and what I would do here is to get valence electrons, you would take the last number, 3, 4, 5, 6, 7, or you can take the numbers, the last numbers. Notice they correlate with the last number there. Be careful, the noble gases are considered not to have valence electrons. So even though you see an 8 here, if you would do a Lewis dot diagram, which I have up here for fluorine showing 8, you know that you have to put the valence electron. So for like neon, you would put not 0, you would show 8 to show that it has a complete octet filled. Okay? So the answer, of course, is the group 2 elements, the alkaline earth metals. So 8 is 3. They're in the same group, same valence electron, same reactivity. Number 9. Which list includes 3 types of chemical formulas for organic compounds? Now, organic compounds, as I've been saying in some of my other questions, they are one of the largest number of molecules and compounds that exist in chemistry. In fact, I would have to say they are, but in fact, the greatest in number because of their carbon chains and their ability to bond to so many other different carbons. So structure is really important here. So we know that structural formulas are important. We want to see exactly how these carbons bond to each other. And that, of course, structure is king. So certainly structural has to be part of that. Now, structural formulas are given to you in different places on the periodic table, but one that people pick up early on and always ask the question, do I have to use this one or this one, is here in Table E. Okay, in Table E, if you look carefully here, the acetate ion, which is the conjugate base of vinegar, okay, is written 2 ways. And people say, which one do I use? And I always said, well, this is a molecular formula, how the molecule is given, how you've been dealing with the rest of the year. And this is a structural formula, showing exactly how they're bonded. And it's very important. The 2 C's are there, the H's are there, and the 2 O's are there, so you can count them up. And you could use either one. It's just in organic chemistry, we want to see the structure. as you write it, because there's going to be so many hydrocarbons that have similar structure, molecular formulas. It's the how they make their structure that gives them their properties. So there's one. As I just mentioned, molecular is what you've been dealing with most of the year. Molecular is in case if I have my propane molecule be C3, and if you count the dashes for H's, it'd be H8. How many of each? You've been dealing with that all year long. Empirical, okay, would be the lowest ratio. Okay, and you say, well, why would I use that? Well, because there are some organic compounds, which are molecular compounds, which are covalently bonded nonmetals to nonmetals sharing, that exist in the lowest ratio. Look at this. CH4 is methane. One carbon in meth has single bonds between other carbons. It doesn't have any other carbons to bond with, so it can't be a double or triple. This is methane. And methane exists in nature with this ratio, as do many other organic compounds. So it can exist in empirical, lowest ratio, structural, or the molecular formula. Okay, isotopic, you haven't heard that or used that for formulas. Empirical you have. Metallic formulas, no. These are not metallic compounds. All right, so 4 is the best answer. 9 is 4. Number 10. Any bond between an atom of carbon and an atom of fluorine. The fluorine atom has a what? Well, you should know that a carbon and fluorine, okay, are both above the staircase to the right of the periodic table, and therefore they're going to be forced to share because they both have strong attractions for each other. This is a covalent bond, non-metal, non-metal. So, careful. Any bond between an atom of carbon and an atom of fluorine, the fluorine atom has a weaker attraction for electrons? I don't think so. Fluorine has a greater attraction because it's off to the right and it's the smallest atom, so it has the largest electronegativity, stronger attraction for electrons. Okay, that's my inclination first. Let's go read all the choices. It's a good idea. Sometimes we'll see something that'll remind you that your first inclination may not be right. Smaller number of first shell electrons. Well, that's not going to be wrong. That's not going to be right. It can't have a smaller, and it can't have a larger number of first shell electrons. Again, if you look at carbon, it's 2-4, has 4 valence electrons. If you look at fluorine, it's 2-7, 7 valence electrons. So there's that staircase I talked about right here, and that delineates between metals, which are on this side, and the nonmetals, which are smaller and have a high attraction for electrons. And I know that because most nonmetals become negatively charged because they love to strip electrons from things that love to lose them. However, in this question, we're dealing with carbon, who's 2-4, and fluorine, 2-7. All right, now if I make this a little bigger so we can see what we're talking about here, they both have the same number of core or kernel electrons. Before you can fill into the second energy level, and they are atoms both filling electrons in the second major or principal energy level, they both have 2 electrons already filled in the first energy level. So that's why choice 3 and 4 can't be right. They both have 2. You didn't know that? Periodic table is your friend here. So smaller number of first shell electrons? No, they both have the same core or shell or kernel electrons. Fluorine has a greater attraction for electrons. And a word for attraction, my friends, is electronegativity. Now, if you weren't sure about electronegativity, I'll just go EN, okay? You can look at somewhere else. Now, I would hope you would know your periodic trends, but if you don't be a fool and not look this up. Electronegativity, which is a fancy word, pinky up if you're writing and saying it. That's my way of saying fancy when you say something, pinky up. In any case, electronegativity for fluorine, okay, is 4.0. Electronegativity for carbon is 2.6. So clearly fluorine has a higher attraction for electrons, and it's a nice resource if you get mixed up with your trends. Number 11, maybe. A sample of carbon dioxide, solid, dry ice, another example of that. Hopefully you saw some in your chem experience this year. And a sample of CO2 gas, can't see that, differ in their what? Well, Their chemical compositions, they have the exact same formula. So they're made of the same ratio and same atoms, so no. They do not have the same empirical formulas. Empirical means the lowest ratio. And they already have the lowest ratio. It's a 1 to 2, so no. They also have the same molecular structures. Now, why is this a molecular? Because this is a carbon and an oxygen, both nonmetals, and this is showing a molecular compound, a molecular structure. So they have the same exact molecular formulas or structures. Now, if you're not sure what the structure is, remember it's carbon dioxide, double bonds with an O, and it double bonds with another O. Only both of that. What's different is how they attract each other. They have different physical properties, and you should know that when you have different phases, this is a physical change. All you're doing is giving the solid more energy for each of these molecules to separate from themselves and become a gas. All right, and that's why sublimation actually occurs at a certain temperature with a certain pressure. And that temperature for CO2 is, I believe, about -80, okay, degrees Celsius. All right, now everything below the -degrees 80 at a pressure of 1, it's not going to sublime. Okay, so number 4 is physical properties. Phase changes. This question is about, do you know that phase changes going from a solid liquid to a gas, they're using sublimation, then you should know that this is sublimation. Again, it's not part of the problem, but it very well could be. Oh, oops, a little doohickey that happens. All right, so go back here. So sublimation is what we're taught. Sublimate. Yeah. Well, okay. Let's get a spelling class going here. Sublimation is when a solid goes directly to a gas, and also you should know that when a gas goes to a solid, you know what that's called? That's part of this course too. It's called deposition. Sounds like we're bringing lawyers into this, but deposition is the name of a gas going to a solid. But these are physical changes, nothing to do with the chemical composition. We're not breaking bonds, we're just changing the attractive forces between them or their distances. Number 12. This is pretty much one of the questions where you're dealing with a vocab. It's an important one. Temperature, you should know, is average kinetic energy. There's many ways to remember this. For me, it's Boltzmann distribution curves. If you were to plot all the motion of molecules, and let's just white out this area here. Look, there goes sublimation there. Let's just white this out. I feel pretty powerful that I can just take out a question like this. Okay, so a Boltzmann distribution curve is one where you take the number of particles, just the number of particles, and you look at their speeds. Now, speed, of course, I can spell here, but speed is their velocity, I would presume, but I'm using a non-vector quantity. Any case, the point being here is that at one particular temperature, this is the distribution of how many particles exist at a certain temperature. Notice around here would be the average. And so we measure temperature. There's going to be molecules that have higher speeds and molecules that have lower speeds. So temperature is just a range or an average of all the different motions. Speed is a what? Is a motion. And the word motion or motion energy is kinetic energy, not potential. So temperature is a measure of the average of all the molecules. Now, it's like a little bar graph. This shows you how many particles are at one speed. And as you can see, as we go away from the average, the number of molecules speed decreases. And this is true because even at a temperature, let's say 50 degrees Celsius, which is pretty warm to us, there's still plenty of molecules that have enough energy to evaporate, even though evaporation, or I should say boiling, doesn't occur to 100 degrees Celsius at 1 atmosphere of pressure. So any case, let's go back to number 12. Which statement defines temperature? Temperature is a measure of the total electromagnetic energy of the particles. Not even close. Temperature is a measure of the total thermal energy. Okay, I like that. Thermal is heat. Heat is kinetic energy. Okay, and The problem with this is it says total thermal energy. Okay, that would be something where you're measuring joules. Joules equals what? Mass times the speed of, sorry, it's times the speed of light. Mass times the specific heat times change of temperature. Okay, so it's the average kinetic energy. Thermal could have been there for kinetic. Okay, they're one and the same. But what got me there was total. No, no, no. We're not measuring total energy. Remember, to get total energy, temperature is only a part of the equation because it's the average times how many you have times how well you change your temperature. Okay, so temperature is a measure of the average kinetic energy, a purely, I would think, a vocab one, but there are some implications you should know from like Boltzmann distribution curves, which is not on the Regents, but however, I think important to understand for that. All right. Any case, number 13, for a chemical reaction, the difference between the potential energy of the products and the potential energy of the reactants is equal to what? All right, now we're into unit, it looks like unit 6 here, which is kinetics. So I'm going to get rid of this right here, this stuff that I'm writing, and I'll get some space for myself and white this out again. I guess I could have whited over that, but I didn't. Okay, so this is a potential energy curve. Unlike the last question, which was talking about motion energy, kinetic or thermal energy, this question is talking about the potential that atoms or molecules have. And this brings up potential energy curves. Whoops, don't want to do that. So potential energy curves, we have the potential energy, which is essentially non-motion energy. And there's so many different types of non-motion energy. Let's just say it's the energy stored in chemical bonds. It's chemical energy. The word stored is used loosely. Some people don't like that. I don't care at this point. So potential energy. So the difference between the potential energy of the products and the potential energy of the reactant is equal to what? Well, let's pretend I have something that can explode. And let's pretend I have, so these are some reactants, okay? And let's do this, H2 plus oxygen. And we know when we make water, water is a very stable compound. And I guess I should balance. We know that the difference of where I start and where I finish, and if you would remember this, the potential energy curve, this is the energy barrier that prevents the reaction from just going from here to here, is our what? Activation energy, right? This is your activation energy. But we're talking about the difference of where we start the energy that we had. It's supposed to be a straight line compared to where we finish. So this is going to be my change, or my delta H enthalpy, or my change of heat, or the heat of reaction. And why did I go down? I went down because energy was lost. This is an exothermic reaction. That's why delta H is negative for these reactions, because you're going down in energy. Energy was obviously released. The extra energy that these guys had individually was lost when they bonded to make strong, strong bonds. Any case, for the now once you drew one, you didn't have to draw an exo and endo, but the bottom line here is that the potential energy of the products, which by the way is this value here, okay, and this is the potential energy of the reactants, you subtract those values and you will get your delta H. So potentially the products minus the potential of the reactants, which could be something that you memorize too, is the heat of reaction choice 2. Okay, which reaction represents sublimation? They kind of implied it with a question a few questions ago, but sublimation is a phase change, a physical change, a solid going directly to a gas. And looking at choice 2, it's the only one. There's nothing for me to teach. It is what it is. Deposition is when a gas goes directly to a solid, and that's not given here. So this is the phase change you needed to know here. Number 14 is 2. Obviously, liquid going to solid is freezing. Liquid going to gas is evaporation or boiling, and gas going to a liquid is condensation. 14 is 2. Number 15. Which statement describes the particles of an ideal gas based on kinetic molecular theory? Okay, KMT, as you teacher might have written, kinetic molecular theory describes the behavior of gases so that they would follow our ideal gas laws that we've been talking about all year. So the way to remember this, I think of ideal versus non-ideal student. If you listen to a few of my videos, that's the way I do it. The ideal student sits up straight, pays attention, winds up being random when people talk to them because they themselves are so focused on the teacher they don't know and have no social skills. The bottom line is they could have People Magazine's most beautiful people to the left and to the right of them. They don't pay attention because they have no attractions for the people around them because they're so focused on the teacher. Now, the real student really cares about the peers around them and they have attractive forces because they are attracted to people around them. So I think of the ideal gas, okay, as ideal student who has no attractions and is random. And if you ask them to get a piece of paper or the set of worksheets for the teacher, they would run in a straight line and bring it back to the teacher as fast as possible because they wouldn't want to miss anything. Whereas the real student, because of their real attractions, if they went to get the same stack of papers, they would go in a curved path and talk to their friends, high five them, and talk to them and take some time. They'd go slower and they would attract and bend more to the people because of their attractions. They really have attractions, really do. That's how to remember this. Okay, so let's go through the choices now that you have the ideal student and the real student in mind. Number one, the motion of a gas particles is orderly and circular. I think you're trying to confuse the Bohr model here. This makes no sense. The gas particles have no attractive forces between them. And you may say, well, why does that make an ideal gas? Because if particles are ideal gases, they're independent particles and they can be random. And if you have thousands and billions and trillions of these particles, random motion will create equal pressure on all four sides of a box. And therefore, pressure is force over an area. If they start attracting each other, like real gases, instead of being independent, they'll go in unison with the other gases, and you wouldn't have collectively the total pressure over an area. You would actually have lowered pressure, as we would talk in another class. So two, based on the kinetic molecular theory, which Satan describes an ideal gas, they have no attractive forces. So think of the ideal student and the real student, and a lot of this will play its hand. Gas particles, number three, are larger than the distances separating them. Larger than the distance separating them. Now, that doesn't make any sense. As gas particles collide, total energy of the system decreases. Now, we know that the collisions are supposed to be elastic in nature. That's inelastic. What number three is trying to state, because there is a postulate for the kinetic molecular theory that talks about that the size of the actual particles is insignificant between the distance of space they fly in. So that's what they were talking about. I couldn't quite grab that in the beginning, but now I get it. And you should know that if I was to draw an example of this right here, I just drew one. You can't see it because they're so small. But if I draw a gas molecule that's 1,000 times bigger, there it goes right next to it. You can't still see it because they're so infinitely small. So the space they fly in and the space they actually take up, when you consider the space they fly in, their own space they take up, we can say their volumes are small. But think with me, the ideal student tend to be what? Smaller students? I'm not sure if I want to get into stereotypes, but one way to remember that. Choice 2, 15. 16. 2 grams of potassium chloride are completely dissolved in a sample of water in a beaker. This solution is a homogeneous mixture. Anytime you dissolve completely, and that's the key word for me, with water, and I know this is soluble from table F, any group 1 ions, okay, make this salt soluble. Water is going to get in and pull that crystal apart with those molecule ion attractions, and the action of the water, the motion of the water attacking these positive and negative ions is going to pull them away and make a solution that has an equal amount of the ions in every area. Homogeneous mixture, my friends in chemistry, is a solution. Okay? And you would write KCl aqueous. And you should know that the K plus will be pulled around by the negative part of the water, which is the H. I call these famous boyfriend, famous girlfriend attractions, where the O's would surround the K plus, which is the negative part of the water, and the chloride ion, which could be the female of the famous couple, the H's, the positive part, electron deficient H's of the water, would surround the chloride ion. So homogeneous mixture, aqueous, again, I'm over teaching, but these are types of other questions you could see. Molecule, ion attractions are what we have in dissolved salts. 16 is 3. 17. Which compound has the strongest H bonding between its molecules? Okay, well, I don't know. We should know that FON is the only type of molecule that has H bonding. So if I look at my choices, the only one that could have it is choice 3. Now, the New York State Regents might break this rule, and the idea here is that something needs to be very, very electronegative and very, very small to create electron deficient H, as I mentioned in my other question. HF fits the bill. Fluorine is very small, which has a very, very high charge density. I pulled electrons in so close, these H's are left really without any electrons, which, by the way, is a proton. And this little proton will attract tremendous amount of things that are negative, because protons being very small with a positive means they're going to have a high charge density. I like to talk about it. We're going to talk about it as Coulomb's law, but things that have a strong hydrogen bonding between its molecules are things that are going to have electron deficient H's and are very electronegative and small. But for this course, the most electronegative atom will create a scenario where we make the H's on the molecule have really no electrons. Therefore, you're exposing a proton, and this can attract other negative parts of molecules. Choice 3, 17. Number 18, powdered sulfur is yellow and powdered iron is gray. When powdered sulfur and powdered iron are mixed at 20 degrees Celsius, the powdered iron is, well, it's not going to become yellow. We're not talking about a chemical reaction. We're talking about making a mixture. 20 degrees Celsius is essentially room temperature. We would need some heat for the activation energy. So they didn't mention that a chemical reaction takes place. And iron's not going to become yellow. You notice things in a mixture retain their individual properties. So we know something special about iron. Unlike sulfur, iron has magnetic properties. So it's going to remain magnetic because it's in a mixture, and the components of a mixture retain their individual properties. And you should know this. Pure sodium is explosive in water. Chlorine gas, okay, is essentially deadly in high quantities. It's a poison. So when you basically react these, they become sodium chloride, which is table salt. And we know how inert table salt is, and of course the reason why, there was a transfer of electrons. Sodium got oxidized, chlorine got reduced, and basically you made Na plus ions attracting chloride ions. And these guys are stable because they have noble gas configurations. So I'm getting off the topic here, but 4 is your answer. 18 is 4. Number 19. An effective collision between reactant particles requires the particles to have the proper, okay, well, an effective collision has 2 components. You have to have enough kinetic energy to overcome the what? Electron clouds that what molecules have that are mostly made up of electrons. 2, which is called activation energy. 2, they have to have proper orientation, because especially in bigger molecules, there's places where bonds can occur and places where bonds can't occur. Case in point, on the ammonia molecule, you got a lone pair of electrons. That is where the action is mostly when it acts as a base. So that lone pair right there is where things have to physically collide in order to bond in that space, like an H plus can coordinate covalent bond. So it's going to have the proper orientation, and the proper kinetic energy, which is basically activation energy. You need enough activation energy in order for a reaction to go. Okay, so choice 4 for number 19. Number 20. Which term is defined as a measure of disorder of a system? Disorder is entropy. It's one of the driving forces in thermodynamics and in the universe. So it's entropy. I don't know how else to say it. Heat, okay, could be measured as joules or Q. Kinetic energy is a form of energy that's motion. Activation energy is the energy required to start a reaction. But entropy is that change in S, measure of disorder of a system. And we know that when things go from a solid to a liquid to a gas, especially the entropy, the delta S, increases. Now, it sounds a lot like enthalpy. Enthalpy is delta H, okay, which is a measure of the change in heat of a reaction, the potential energy change. Okay, so very important. Entropy is a measure of chaos of disorder, number 2. So number 21, as we move on through the first part, which process is used to determine the concentration of an acid? Okay, so these are all forms of laboratory techniques that you should be aware of. Let's start with distillation. Distillation is where we take a mixture of liquids and we separate them based on their individual properties that they retain because they're not bonded. Components of a mixture retain their individual properties. So we separate them physically by boiling off the one liquid that has a unique boiling point that the other liquids do not. And that's basically what we do. We boil off, let's say, water from alcohol or the water from Coke that we did in class, and we leave behind all the other components. Okay, and of course you can pull that water out by making it condense in a cooling tube and collecting that liquid. All right, chromatography is another physical separation based upon differences in solubility with a usual mobile phase and a solid phase with differences in their attractive forces based on London dispersion forces and polar. So chromatography, like you could separate all the different colors that make up the ink, okay? Or in the case in class, we separated in grape Kool-Aid, we separated the red from the blue by their differences in solubility in different concentrations of alcohols. It's a physical separation based on solubility. Electrolysis is what we did in redox, where we used a battery and we separated and made the pure forms of a salt, okay, by adding energy to a non-spontaneous process. Okay, number 4 is the titration, where we use sometimes called the titration formula, where we used MV of the acid equals MV of the base. Sometimes people use MA, MB, molarity of the base and volume of the base. And what we did here is we knew the volume of our acid. Okay, I won't use that again. We knew the volume of our acid. We didn't know the molarity, but knowing the volume of the base that was needed to neutralize the acid and knowing the molarity of the standard base, we came up with these 3 variables and solved for the molarity of the unknown acid. Of course, this works because you're matching, in this case, hydroxides with H pluses, protons. So titration is a laboratory technique that you used using a burette, an emptying device. Maybe you used phenolphthalein as your indicator to tell you the endpoint where the hydroxides equaled. Okay, any case, number 21 is 4. Have to be able to identify these laboratory techniques. 22, the compounds have different functional groups. Functional groups is table R. These compounds have different, well, as I've been saying in many equations, structure, maybe, structure is king. So you have a different structure, you have a different, okay, physical and chemical properties. Okay, so in any case, Therefore, these compounds have different chemical properties. Absolutely. Gram formula masses, that'd be a no, because if you notice, they actually have the same number of carbons. These are both C2, H6O. They both have the same molecular formulas, but different structural formulas. These guys are called isomers. Okay, even though they're not mentioning it here, they're implying it. These are isomers. Structure is king. Change the structure, change the chemical form. That's why the IUPAC naming system is based on the structure, because writing this alone, you could wind up in a very, very bad scenario, especially 1-propanol and 2-propanol. So they don't have percent composition of mass? No, because they have the same what? Makeup. Numbers of atom per molecule? No, for the same reason. Remember, they're isomers, so all of these for isomers would be no. Same formula, different structure. So 22 is 1. 23, which term identifies, get into redox now, which term identifies the half reaction that occurs at the anode of an operating electrochemical cell? Okay, the anode. Now we know from a very cool mnemonic, maybe not that cool, anox, red cat. So when I think of anode, I think of oxidation. Anox, red cat. The cathode, okay, as you probably already know, is the place of reduction. So the anode is always a place where there's a loss of electrons. So number 1 is oxidation. Neutralization is acid-base. Transmutation is where a nuclei, unstable, changes into a new one by emitting alpha-beta particles or positrons. So that's no longer there. Reduction would be for the cathode, red cat. So 23 is 1. 24. During the operation of a voltaic cell, this is a battery. You should know your history here. Alessandro Volta and Luigi Galvani, where two people had an argument about what was creating the legs of frogs to contract when static electricity was put on. And Alessandro Volta created a device called now a battery, sometimes now called a voltaic cell, to show the Luigi Galvani that the frog legs were moving because of a physical property of matter, not biological. So in any case, it's a battery, and batteries produce electrical energy spontaneously. Now the word spontaneously means don't think it just happens by itself. It happens because of an arrangement of the correct chemicals. But spontaneous is a direction, and it means that direction is happening. Is the battery working? So here, spontaneous, a nice way to think of it is it working? Okay, and that's one way to do it. So during the operation, the cell produces electrical energy spontaneously. That's the whole idea behind the battery. If it produced chemical energy spontaneously, you'd be making some kind of chemical reaction by itself. Now, it's producing electrical energy. It's creating a potential difference called a voltage, sometimes called an electromotive force. Electrical energy, it's non-spontaneously, that would not make any sense. Batteries are working. Chemical energy, no. The best answer here, and some of these are kind of gibberish here, 2, 3, and 4, is you're creating electricity. Now, if they said electrolytic cell, you would say that chemical energy was made from a battery or non-spontaneously. Okay, because electrolytic cell requires energy. So 24 is 1. And I guess number 4 would be the best choice for an electrolytic cell. Look at the word electrolytic cell. This one requires a battery. Electroplating, electrolysis of a fused salt. So you're creating a chemical reaction non-spontaneously because you need a battery to make it happen. So this is the voltaic cell, it's the battery. These two make no sense. Number 25, in which type of reaction are electrons transferred? Now this is a very important term, transfer. This screams to you ionic bonding, as we've learned previously. Transfer of electrons, meaning some chemical species is good at losing electrons, and that means someone's good at what? Gaining electrons. So there's a complete transfer. We know our metals tend to lose them because they're big radii. Electrons are usually farther away, and they have low attraction for the electrons, called electronegativity. And of course, we know our nonmetals, okay, love to gain them because of their smaller atomic radii, which is due to a high attraction, high electronegativity. And when you have that, you've got yourself usually an ionic bond. Case in point, Na with 1 valence, and of course, let's say chlorine with its 7 valence electrons. And because of the greater electronegativity, it takes that electron, you make ions, and Na becomes Na plus. And you've learned this, but now you should have also understood that this is something called a redox reaction. This becomes -1. And the bond between them is ionic right here because you've made ions by losing and gaining. But losing and gaining, okay, means you have oxidation and you've got reduction. And when you put the two words together, well, red and ox, you get a redox reaction. Okay, all about the electrons being transferred. So the oxidation reduction reaction is what we're talking about here, all right, in terms of these types of reaction. And something you just really have to know and be able to identify, but there is a mnemonic possibly that you may have learned. Leo the lion says grr, very famous mnemonic, and basically means losing electrons is oxidation and gaining electrons is reduction. Okay, so it's an oxidation reduction reaction. And the rest of these are kind of off the topic. Organic addition, organic reactions you should know are basically covalent in nature. And covalent in nature are not a transfer as we've talked about here. But this would be sharing, so you wouldn't have someone gaining and losing electrons. They'd be kind of sharing them. Double replacement, okay, that's another reaction where the ions of one element are replaced with the ions of another, and they call it double replacement because essentially everyone is do-si-doing, so to speak. All right, so you have sodium chloride, let's say with potassium iodide, and you would be just switching ions. This positive and these metals are positive, the halogens are minus, and all you'd be doing is this positive would now go with this negative and vice versa. And it's not a redox reaction because the ions, the charges of the elements stay the same. Acid-base neutralization on this level is considered not to be a redox reaction because, again, it's essentially a double replacement. Acid, base, and a salt, if you were to take, let's say, your hydrochloric acid, and you would take your NaOH, well, you can consider that the H to be positive, the chlorine to be negative, Na to be positive, and the hydroxide to be negative. You can consider this to be like a double replacement. So this positive goes with this negative to make your water, HOH, you can write it. And you could put Na plus with the NaCl. And if you notice, nobody's charges have changed. So you can think of an acid-base neutralization reaction, especially strong acid, strong base, to be a double replacement. Okay, and again, what we're teaching, acid plus base is salt and water. So essentially, these two are very similar. Okay, so that's the answer. Best choice is 2, clearly. Number 26, a substance that dissolves in water and produces hydronium ions. Now, this sounds a lot like hydroxide. Don't confuse yourself. The hydronium ion, as listed in Table E. Table E I call the what the heck is that table because you may run into things that you forget. And the hydronium ion listed right there, H3O plus. It sounds a lot like the hydroxide, but don't confuse them. Okay, hydronium ion is essentially made from a water molecule with the 2 lone pairs, accepts protons. Okay, and these protons are able to bond with this lone pair. So you can think of water holding onto an H plus that is always generated by acids, no matter what definition you want to believe or work with. Okay, the Arrhenius definition produces the H pluses, and of course this is what bonds with the water. So an H3O plus is synonymous in terms of pH with the H plus. More realistic example of having protons in water than the free protons that Arrhenius stated. In any case, so this is due to acidic properties of molecules that are generating protons that the water is holding on to, not the hydroxide, not the base. So knowing that hydronium ions are the H3O plus that you could look at table E, and knowing that the hydronium ions are water holding on to what? A proton that came from acids, you should know that the hydronium ions, okay, are a direct result of having an acid in solution. Alcohols are not acids or bases. In table R, they have an OH. In truth, there's some little tiny bit of acidity here with that H, but we don't consider that in this course. Okay, a base, of course, is something, and the Arrhenius definition gives you either hydroxides in solution or lowers the pH. A salt, and again, in this course we don't deal with acidic or basic salts, so we deal with salts like NaCl as neutral in this course. All right, that's why number 2 is the answer. NaCl does not have acidic or basic properties, so the pH of this compound would be 7. Number 26 is 2. Number 27, according to one acid-base theory, notice we're in the acid-base part of the questions of the test, a base is a what? Well, we know the Arrhenius definition, with this most simplest, least in scope, suggests that you produce OH minus as the only thing in solution. Okay? Now, a better definition that encompasses all the earlier definitions is the Bronsted-Lowry definition, which you don't have to know by name, that says to be a base, you are a proton acceptor. We know the hydroxide can accept a proton because when it does, it makes water, and we call that neutralization. So bases are H plus ion acceptors. Okay, so it's an H plus acceptor. Now, if you get yourself crazy about learning names, you shouldn't. The easiest definition, Arrhenius. To be a base, you have to produce hydroxides. To be an acid, you produce protons. But the other, better definition explains other chemicals that are basic and acidic that don't quite do that. Case in point, in your table, I believe table K, I am mistaken, not table K. Oops. I am mistaken. It's not table K. That's your acids are listed. Table L is your bases. And you can see that ammonia is listed as a base. This is the Arrhenius definition. These hydroxides, these all have the OHs with a metal. These are all Arrhenius bases. This one doesn't have a hydroxide, so how does it act as a base? Well, as your teacher probably showed you, ammonia reacts with water, and its lone pair, which drives its chemistry, is able to attract electron deficient H from water. It can pull or ionize water, and electrons flow from the water. Water is acting as an acid. This is acting as a base because the acid is giving off an H plus. And what you make is an NH4 plus. Notice it became positive as it gained a proton or an H plus, and the water lost one, and it's a hydroxide. So indirectly, ammonia produced a hydroxide, and that's why we consider it to be a base. It actually would be a Bronsted-Lowry base because it's accepting a proton. So an accepting a proton or donating a proton is another acid-base theory beyond the Arrhenius definition. So 27, clearly hydroxides or bases like ammonia, NH3, okay, can accept protons, H pluses, number 1. Number 28, which compound is an electrolyte? Okay, an electrolyte are things that dissolved in water conduct electricity, and they are due to free ions. So anytime you have ions that are free in solution, these ions conduct electricity. Now you may say, well, why? Now I think understanding why helps us understand and remember. if you've got ions in a solution, just really quick here, and I've got positives, okay, and negatives, okay, equally distributed throughout my solution. These are ions. And I was to put in an object like a, I don't know, electrical end of a cord here that's very, very negative. What would happen in my beaker is that all of the positive ions who are free to move would do what? Would migrate down to the, I guess this magenta negatively charged object, and what would happen is all of the positives would move toward the negatives, and that would leave a scenario where this side of the beaker is being kind of balanced with these negatives here, and the other side of the beaker, you'd have the negatives who are repelled by these negatives here, and you can see that the charge got conducted. The charge was over here, and by the positive ions migrating to the negatives, and then negatives repelling that charge, you've created a place in the beaker that's negatively charged. You would say that charge was conducted, but the ions have to flow. So the question is, who has free ions? Now you should know that number one, salts, things that are ionic are made of ions, and if they're soluble, they break apart into free ions. For instance, sodium chloride, we know is a free ion, or is a soluble salt, I should say, breaks apart to Na plus and Cl negative. All right, so another thing that produces ions is acids. Acids dissociate into H pluses. So HCl, a strong acid, breaks apart into H plus and its conjugate base Cl negative. And these are the free ions that could be here. And of course, bases also are great electrolytes, especially if they're strong. Sodium hydroxide dissociates into Na plus and Cl negative. So we're looking for either a salt, an acid, or a base. Look at your choices, and you see that the only thing here that looks faintly familiar would be choice 2 and choice 4. Now you look at choice 4, right from table L, that's a base that's listed, and that's your answer. There it is, common bases. Notice it has a hydroxide with a what? With a metal. It's listed right there. Now they seem to always want you to pick, and they throw something called an alcohol. This looks like it's a base too. Why not choice 4? Well, because, my friends, in chemistry, this is an alcohol. This is not a base. Although you see something called you may see this OH, this is a hydroxyl compound. This is bonded covalently and does not dissociate as a free ion. So this is not a base. So you remember that all alcohols are listed in table R. So here I am at table R, and although this looks like a hydroxide, it is not. It's bonded covalently, and these are alcohols with an OL ending. They're bonded covalently, and these are not things that slough off. To note if you have an alcohol, here's a general formula: the rest of an organic compound. So if you see carbons and hydrogens of some amount, and you see the OH, these are nonmetals. So if these are the nonmetal part, and that's your R, then you know it's an alcohol. If you see metals, okay, that are good at losing and gaining electron with the hydroxide, you know that to be a base and not an alcohol. So the carbons and hydrogens with the hydroxide are not bases. So 4 is the answer, and here we put it right there. Number 4, not the alcohol. Number 30, actually 29. Number 29, which identifies a type of nuclear reaction. Now, a nuclear reaction means that you have reactions where you're dealing with the nucleus of an atom, not the electrons. These reactions have a lot more energy because you're dealing with the strongest force in nature of all things, called the strong force, which is stronger than the electrostatic attractions between protons and electrons. Any case, going through these, number 1 is fermentation. This is an organic reaction where we produce alcohols that are listed in table R. from yeast. The zymase in yeast produces two alcohol molecules and a CO2, and fermentation is not that. Deposition is not a chemical reaction. This is a physical change where a gas goes directly into a solid. Greatest example of that is snowing. Reduction is half of the redox reaction where we're gaining electrons. And of course, fermentation 1 and 3 reduction deal with electrons. Deposition is a physical change, so it makes no sense here. Fission, okay, is splitting the atom. And that is where we're taking something like uranium, okay, atomic number 92, 235 is a fissionable material. And with a small, slow-moving neutron, a mass of 1, a charge of 0, this splits into smaller number of elements. We could have xenon, it's 854, and we could have, I guess, maybe barium, atomic number 56. Okay, with some more neutrons, and I'm just making this off the top of my head, but I'm splitting this up into more smaller atoms here, and this might not be terrifically balanced, but, and you don't have to know this top of your head in terms of making the reaction, but you should see a large nuclei being split into smaller, producing more neutrons, 2 or 3, okay? Fission is a nuclear reaction, and where we deal with nuclear equations like that, where atoms are being split. Number 30, which radioisotopes have the same decay mode and half-lives greater than an hour? So when you ask for information, something like this, you should know there's some place to go, and table N is your friend. So the question again, which radioisotopes, these are radioactive isotopes of elements, have the same decay mode, okay, which means they are either giving off an alpha particle, a beta particle, a positron, all right? And these are the particles listed in table O, or as we'd say, table O, okay, depending on what part of the country you're from. So to know which particles they're given off, we go to table N. Na. So let's go see in table N which ones are the same. So table N, here we go, and I see that my gold 198, this specific isotope of gold, has a B negative decay mode, which is a beta particle listed in table O, if you needed to know what that was. And nitrogen 16, also this particular isotope of nitrogen also gives a beta particle. Okay, and as we go through that, let's go to table O. If I knew my alphabet, life would be easier. And if you look at table O from a previous question, that B negative here is that beta particle. I also call that an electron, a high-speed electron. And there it is. So a beta particle is a B negative. Not that you needed to know that, but if they said what type of particle, table O is your friend. Any case, getting back to the question here, because I could have made a mistake if I did not read carefully, they wanted the same decay mode, and they wanted half-lives, which are listed in table N as well, that are greater than an hour. So let's go back to our table again, and I have basically color-coded. We had gold 198, which is a beta decay, and we had, where are we? Nitrogen 16 beta, but this is 7.3 seconds, so that's not greater than an hour. Then we had calcium 37 and iron 53. Both are positron decay, which is good, they're the same, but this is less than an hour, so is this. So we're left with 2. Iodine 131 is 8 days, and P32 is 14 days, this half-life, and they're both beta decayers, so this is the pair you want. Technetium 99 and uranium 233 are different decay modes, so you can't use that. So the winner is going to be the one with the same decay mode, in this case beta particle, and half-lives that are greater than an hour, are the iodine 131 and P32. So choice 3 is the answer here. So now we head into part B1 section of the course. Part A is over. The first 30 or so multiple choice questions are part A, and these typically are the easier of the questions. These are usually one concept based questions. Part B1 in theory is supposed to be multiple concept questions or questions that have possibly more than one step. Sometimes I see that, sometimes I don't. But in any case, at number 31, still multiple choice section because the first 50 are so. The diagram below represents the bright line spectrum of 4 elements and a bright line spectrum produced by a mixture of these 3 elements. Now you should have learned that these bright line spectrum represents particular wavelengths of visible light that are emitted when electrons from a positive nucleus jump back to their ground state. So you have a nucleus that's positive and you've got, let's say, shells of electrons. I want to think of it that way. Now they're not circular orbits, but I'm just using that as an example. Electrons that are closer have lower energy than electrons that are farther away. So electrons here, okay, have lower energy, and electrons farther away have higher energy. And what happens is they absorb energy, they jump to energy levels that can exist farther away, and they're unstable because of the high energy, and they need high energy to pull away from this positive nucleus. But because they're unstable with high energy, they eventually leap back. These quantum leaps of an exact energy give off light or spectrum in exact wavelengths, which is representative of certain exact energy. So every unique element has a unique bunch of spectral lines that represent their unique leaps backward from their different energy positions. And now every unique element has a unique energy position because they have a unique number of protons and electrons that interfere. So element A has these lines that represent the different leaps backwards, and D has these lines. So if you've got a mixture of these elements or some of these elements listed, you should know that they were going to retain, and mixtures always retain their individual properties unless they bond. So a mixture of the elements or compounds are always going to have their own individual properties still holding on because they haven't changed. So we're looking for lines that are in different elements. So I know element A is here because its lines are there. Okay, who else is there? Okay, it looks like element D is there as well. So it looks like all the lines are from element A and element D, if I'm not mistaken. Maybe Z is involved. Yeah, Z too. So A, D, and Z are involved here. So which is not in, so this line comes from the Z, this line comes from the Z. Looks like X is not involved. So element X is not involved, and 31 is X. Is 3. All right, 32. What is the overall charge of an ion that has 12 protons, 10 electrons, and 14 neutrons? Well, I know that 14 neutrons are neutral. Table O tells me so. In table O, you'll see an N, you'll see a 1, and a 0. That bottom number is charge. If I forget, electrons are -1 charge because you'll see them listed as a beta particle, and you'll know that protons are listed like this. They've got a +1 charge. So if I'm looking for the overall charge, I know that this, okay, represents a -10, okay, and this gives me a +12. Put them together and you're going to get a +2. And you could see that atomic number 12 is magnesium, and magnesium loves to become +2. And there it is. Magnesium loves to become +2, loves to lose its 2 valence, and becomes +2 because it has what? 12 protons. And by losing 2 electrons, it still has 12 protons, right? It starts out with 12 protons and 12 electrons as an atom. And when it becomes an ion, it loses 2 electrons, gets oxidized, and has 10 electrons. And the whole thing now is +2 because of that. Number 33. As the elements in period 3 are considered in order of increasing atomic number, there's a general decrease in. Okay, couple of hints here. Period 3, that you should know is a row, and that's the same thing, row 3. Or you could say it's the principal energy level designated by the letter n. N equals 3. So you hear period 3, rho equals 3, n equals 3. They're synonymous. It's the third major energy level, sometimes called a principal, okay? A principal energy level, okay? And this is the third. All synonyms here. Now, if you're saying there is an increasing atomic number of the rho, you're going across. So as we go from lithium all the way to, let's make it neon, okay, atomic number 3, 3 to atomic number 10, what's happening here? Well, as you probably have guessed, and you should learn, as we go toward the nonmetals, our atomic radii get smaller. And they get smaller because the nuclear charge, which is the charge in the nucleus, which is due to the number of protons, increases. And they could ask you, who has a greater nuclear charge? And you would say neon. It's got what? Atomic number 10, which is the protons. So as you increase the number of protons in the same shell, in the same row, in the same n equals 3, in the same principal energy level, or in the same period, okay, these electrons are being pulled closer to the positive nucleus. And we would say the attraction for electrons increases. But here, there's a general decrease in, of course, atomic radius. That is your answer, and that's one of the most important trends on the periodic table. It's because the radius gets smaller, because of the nuclear effects or the charge of the nucleus is pulling in those outermost electrons. It's reason why the smaller atoms are your nonmetals. It's the reason why nonmetals tend to gain electron because of their tremendous attractions. Now, as an aside, as you go down a group, as you go from lithium to sodium, the nuclei the atomic radii, I should say, get bigger. And that's not because of more protons, because sodium, in this case, has 11 protons. So you may say, well, why does it get bigger as you go down? Well, it's because as you go down, you're adding an extra shell. Lithium is 2-1. So it's got only 2 shells that are occupying electrons. This is 2-8-1. The third shell, you're adding a third shell. Yes, there's more protons, and yes, they're pulled, but this outermost electron is in a third shell. It's a little bit farther away, and also you can also consider that being in the third shell, these electrons are being shielded by the second shell that has 8. Harder for this positive nucleus to feel that outermost electron in the third shell if it's got to get through the other electrons that are negative. These negatives in here make it really hard for this positive nucleus to get through that, and really hard for this electron to feel that nucleus, so it's easily removed or it moves a little farther out. A couple of different ways to think about that. But clearly atomic radius is decreasing. Very important you understand that. But even if you forgot that, there's a place to look. So table S is our friend again. Notice it gives you atomic radius. So as you go from lithium, I'm going across the period to beryllium, to boron, to carbon, to nitrogen, to oxygen, to fluorine, and neon. These, of course, are in the period 2 that we just talked about. And if we make this smaller, and you can see this is what I'm talking about here. I'm going from lithium, beryllium, okay, to boron, don't be one, carbon, nitrogen, oxygen, fluorine, neon. This is period 2. Notice this number here, okay? So very important. So what's happening to the size of the atomic radius? Look, lithium is 130, beryllium is 99, 84, 75, 71, 64. You can see the atomic radius gets smaller as you add more protons. Notice it also gives you electronegativity, the attraction for electrons, and first ionization energy, the amount of energy it takes to pull one electron away. These two depend upon the atomic radii trends. Obviously, the smaller you get, okay, the smaller you get, let's say fluorine, neon wouldn't have any electronegativity because it's stable. the more attractions you have for electrons, and the larger amount of energy it would take to pull the first electron away. So clearly the answer is number 2 for 33. Number 34. Which electron configuration represents electrons of a sulfur atom in the excited state? Okay, the idea here, or the most important piece of information, is the word atom. That tells me it's not an ion, which means protons equal electrons. So the first thing I'm going to do is find my sulfur atom from the periodic table. And there she is, a non-metal above this staircase. And what I see from the sulfur atom, it's a 32 and a 16. So sulfur rounds off to an atomic mass of 32, and it has, of course, an atomic number of 16. Now what's important to me is this is 16 protons, and because I said the word atom, it also means that the electrons have to equal the protons to be neutral. Atom means neutral. So this is 16 protons, and if it's an atom and not charged, it also equals its electrons. So I know it has 16 protons, I know it has 16 electrons. That's important in this question. So being atomic number 16, I know it has 16 electrons. Okay, so therefore my excited state, which an electron configuration is what we're looking for, has to only have 16 electrons. Now the excited state means that electrons have, or the part of the atom, some part of the atom gained electricity, absorbed energy, it could be electricity, which is a form of energy, and electrons jumped farther away. As I previously discussed, we can have a positive nucleus, and we can have these shells of electrons, and now of course I'm using the distance. Electrons that are closer have lower energy. When they gain electricity or they gain energy, keep saying I'm stuck on that, they jump to shells that are farther away from the nucleus, which have higher energy. Now, why would they have higher energy? Because they have to overcome the what? The attractive force of the protons. Electrons are negative, protons are positive. To go farther away, you need energy to be absorbed to overcome this electrostatic attraction. But when you have the energy, you're excitable, you have higher energy. So we're looking for an electron configuration with 16 electrons and is going out of order. Now, the reason why I say out of order is because electrons normally fill from lower energy shells first before they fill the higher energy. Electrons will go to the path of least resistance. So electrons will fill lower energy shells first. So we have to see which one does that. Looking at number 1. We know that 2 fills the first energy level, and then I know that 8 fills the second. But wait a minute, for me to have 6 in the third, I'm supposed to have 8 first. This is an excited state showing electrons going out of order. Well, so does number 2. Number 2 has 7 in the third energy level, yet there's only 7 in the third. This is supposed to be 8 as well. Choice 3 and choice 4 are not excited state. These are called ground state. Now what makes them ground state is that they're low energy, they're filling in order. We have 6 in the third only after we have 8 in the second, meaning once I fill 2-8, the 6 is filled. And you can see that if you go through the periodic table, they fill in order. So back here, so which one is sulfur? Well, which one is 16 electrons? So if you look at number 1, 6 plus 2 is 8. 8 plus 16 is 14 electrons. Okay, this is the excited state of an element with 14 electrons. This is the excited state of silicon. How do I know? Silicon has atomic number 14, and as I said, the atomic number equals the electrons if it's an atom. Atoms are what? Neutral. So the second choice, I bet, has our perfect number 16. 7 plus 2 is 9. 9 plus 7 is 16. This one has 16 electrons and is 16 electrons and is excited because that should be 2-8-6. 1 electron from the second energy level jumped to the third when energy was absorbed. So the best answer here is choice 2, the only answer. That's the only one that is sulfur in the what? In the excited state. Notice this other one here. Number 4 is sulfur because this equals 16 electrons as well, but it is in the ground state. Number 34 is 2. Number 35, given the word equation sodium chloride, and oxygen, what type of reaction is represented by this equation? Well, I know that it can't be double replacement. And the reason I know is I only see one reactant. Double replacement is when you have two reactants that are switching their ions, hence the word double. Okay? Single replacement, you still require two elements to switch. Okay, so that can't be single replacement. Synthesis implies that we're making something from its elements. Okay, so that can't be right because we're actually breaking something down. And number 3, decomposition, okay, is the best answer. We're taking a salt and we're breaking it down into smaller pieces. That's decomposition. Synthesis would be the opposite direction. So if we start with oxygen to sodium chloride, you could make a case for synthesizing that one compound. Okay, so this is decomposition, breaking down. And you can see a bunch of these examples in table I in the middle. Looking at table I, okay, the first third here is combustion reactions, and then if you look at the second half, you've got synthesis reactions where you take in usually the elemental forms and creating one thing. The opposite of that is decomposition. But I also will state if you had a part 2 question and they said what kind of reaction is this, if they went forward or backwards and you got confused, you can also say these are redox reactions. How do I know? Well, one quick way is to identify a standalone element, either by itself or bonded to itself. They are given a 0. Why? Because I keep saying atoms of elements are neutral. Protons equal electrons. And if there is 0 on one side and they're bonded to something, there's something other than a 0. That means they're what? Oxidation numbers are changing, which means electrons are being passed around. So all you have to do to identify a redox reaction is find yourself an element bonded to itself or an element hanging out by itself. There's zeros, which means they're, in this case, starting 0, and they become something other than 0. That means their charges are changing. Electrons are passed around. Notice I said this was combustion, my friends, in chemistry. It's also redox. Look at this oxygen. These are all zeros. If I go down the bottom third, these are ionization reactions. These are not redox. You can call these decomposition, but we like to call this ionization reactions, where a salt, if it's soluble, decomposes into its ions. Notice they're retaining the same charges they had in the compound, so these are not redox. 35 is definitely 3. Now, again, double replacement, I've drawn examples. Single replacement is kind of like our zinc plus hydrochloric acid, which we would single replace to make zinc chloride plus hydrogen gas. Let's balance that off. We need 2 of those. Okay, and then double replacement, real quick, could be something like lead nitrate. That's a polyatomic ion, lead 2 nitrate plus potassium iodide. And you're going to switch partners. So you're going to make lead iodide, which is a yellow precipitate. It's your solid, plus KNO3, which would be your aqueous. And all you can see is that the partners are just changing. The lead plus 2, still lead plus 2. The nitrate hooks up with the K. All you're doing is switching partners. Single replacement, double replacement. Number 36. Number 36, which compound has the highest percent composition by mass of strontium? Percent composition by mass. Okay, as you probably have done in your class, a percent is made by a what? A part over a total times 100. Okay, table T will show you this. So we're trying to figure out who is going to have the greatest percentage by mass of strontium. Now you could probably look at this and try to finagle it in terms of how light the other compounds are. But probably the safest bet here is to go through this question and do a percent by mass of all of them so you don't get confused. So let's white this out here, give us some room. All right, and let's think about it. Well, strontium and strontium chloride. Now, we're doing a percentage, so it doesn't matter what size sample we pick, but I'm going to pick 1 mole. And I know something very special. 1 mole of any atom or compound is equal to its formula mass. That's the mass of all the elements, atomic masses. So in number 1, strontium chloride, let's go find strontium and chlorine from the periodic table. So strontium is 44.9. We can round off to the most common isotope of, upset, that's scanned. That's not, I can read, huh? Strontium, let's do the right chemical element. Okay, my short-term memory's gone at this height. We're doing not scandium, we're doing strontium. 87.67 is 88. So strontium is 88. Let's go find chlorine. Chlorine is 35.4, so we can round that to 35 if you like. So chlorine is 35. And what we do to find our part, we're talking about strontium. There's only 1 strontium, so I put an 88, it's only one of them there, over the total mass. That's 1 strontium and 2 chlorines. So I'm going to take 35 times 2, and the reason why it's 35 times 2 is because in the formula, in number 1, there's 2 chlorines. 35 times 2, 70, plus how many strontiums do I have? I have 1. So plus an 88, and I'm assuming in 1 mole of this compound is what my assumption here is when I do a percentage, I'm making an assumption I have 1 mole of all the compounds. And 1 mole of this, I have 2 moles of chlorine, which is 2 times 35, 70 plus 1 strontium, which is in this case 158. You could times it by 100 if you want to make a percentage, and you got 88 divided by 158, and what you get times 100 is 55.7%. All right, so 55, we'll just make it 57% of the total mass of this compound. Okay, we're running a little faster now. Strontium iodide. Now, iodide or iodine, we go to the periodic table, and when we round off, we're going to get 127. Okay, for time purposes, we go to the periodic table, you find iodine, it's 127. So iodine is 127. So we have 2 of these. So 2 times 127, and I get 254 plus 1 strontium. 1 strontium plus 88. That gives me 342. All right, so 342, you can see that the bottom number is bigger, and there's only 1 strontium, so times it by 100, we're going to get a lower percentage. You can see how this is working here. Divided by 342. And times by 100, you get 26%. So this one is 26%. This is 57%. And you know what? Let's continue on. Number 3, I have strontium with oxygen. Now strontium is 88, but now this is going to just be 88 plus the mass of oxygen, if you go to the periodic table, is going to be 16 when you round off. There's only 1 of them. So this becomes 104. Notice the bottom number is getting smaller, which means this 88 is a bigger fraction. Times that by 100, of course that's going to be bigger. 88 divided by 104, and you get 85%. What about sulfur? The last one I don't have to do because it's going to be 88. You go to sulfur on your periodic table, and you get 32. And 32 is a lot, what? It's a little bit bigger than the oxygen, 16. So this number will be bigger than 104. If you don't trust it, 32 plus 88 is going to be 120. So this number is going to be bigger than this number, so the percentage will be smaller. But if you don't trust it, you can do 88 divided by, in this case, 88 plus what? 32. And you get 73%. So you might have been able to think this one out, seeing how much of the other chemical, but some people don't like that. Go through the math. percent by mass is important. The one with the greatest or highest is the one with the smallest number on the bottom, and being only one oxygen, being 16 plus the 88, would give this the highest percent by mass. Choice 3 is the answer. Number 37 states how many pairs of electrons are shared. Shared is a covalent bond. So if I look between the N is one bond. That bond represents a pair of electrons that are being shared. So there is one pair. If it's a double bond, like say oxygen, sometimes they draw it like this. That would mean you'd have two pairs, because when you do the Lewis dot structure, okay, you would see that each oxygen needs a pair to have that stable octet that we talk about. So that's each pair of electrons, okay, is a dash or a bond. So that's one bond, it's one pair. Choice 1 is the answer for 37. Number 38, which formulas represent one ionic compound and one molecular compound? Very important you know this. An ionic compound is a compound that deals with ions. Now, we normally say metal and non-metal bonding. And the reason why a lot of people would say non-metal, and that's of course if you can spell it, non-metal, is because metals tend to what? Lose electrons, get oxidized, non-metals gain. So because of that, there's going to be a what? A transfer of electrons. And you're going to make positive ions attracting negative ions. And we call the bond between them, ionic. So if I want to look for my ionic compounds, I'm looking for metal, non-metal. Now, you may say, I don't know that. So let's go to the periodic table. On the table, you've got a staircase here. This staircase separates the small atoms that are nonmetals by the what? By the metals. So all of these here are metals. How do I know? They all become positively charged by losing electrons. Who do they lose them to? They lose them to the elements that get negative by gaining them. And these are the what? The nonmetals. Okay, so that's very, very important you understand that. A molecular compound is a compound that makes molecules. It's a fancy word for something covalent. Covalent means you have nonmetal above the staircase bonded to nonmetal. And these guys are forced to share electrons. Why are they forced to share? Because they both have high electronegativities. So they're both fighting for them. Nonmetals have a high electronegativity. Metals have a low electronegativity. So that's why you have a transfer in this case. So who's molecular? Okay, well there is a nonmetal and nonmetal, 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 nonmetal. These are all molecular. And notice something, hydrogen is a nonmetal, even though it's not really above the staircase. It's separated from the reference table, but hydrogen is included as a nonmetal. Okay, who else is a molecular? Well, nitrogen and oxygen, both above the staircase. And who is a ionic compound? Well, barium sulfate is. You have your what? You have your metal, which is usually a dead giveaway. In this case, we have a bunch of nonmetals called a polyatomic ion, but this is also ionic. This is ionic as well. Even though it's also a base, it's a fancy type of salt called a base. It is a metal bonded to another polyatomic ion that's negative, but they stick together because of their attractions. And of course, barium chloride is your metal, nonmetal. And that's your answer because we have a salt, which is a fancy word for something ionic. And we have our molecule, which is which they make. And you should know that covalent compounds make distinct molecules, like water. Here's one molecule, distinct number, distinct shape. Ionic compounds make crystals. They don't make molecules. We might write NaCl as a metal, nonmetal salt. That's a solid, but there's the Na plus attracting the negative, and it keeps going. Na plus attracting this negative, attracting a positive, and this grows in 3 dimensions. It's a crystal. All right, so the answer is 3. Number 39. Which Kelvin temperature is equal to 200 degrees Celsius? Okay, well, this is a converting between Kelvin and Celsius, and this is a table T question. Let's go see what they give us. Table T is given to us. It's the last page of your reference table. It gives you some important formulas that you could be using already, but among those, it gives us our temperature conversion. So we know that Kelvin equals Celsius plus 273. So in our question, they said, what is the Kelvin conversion? Well, they gave me the Celsius temperature to be 200. So you plug it in for C. Therefore, you're just adding 273 to it. So 200 plus 273 is 473 kelvins. That's all you're doing. Remember, the Kelvin doesn't get a degree sign because it's using the Celsius scale, right? Celsius and Kelvin. Kelvin used the Celsius scale. He just started his 0, what? 273 degrees sooner. He discovered the coldest possible temperature was negative 273, and he made that the absolute 0. Okay, a little bit of background and fun there. So 39 is a 4. I think that might be our second math question. Okay, number 40. Here we go with a third math question, if I'm not mistaken. A 10-gram sample of water at 23 degrees Celsius absorbs 209 joules of heat. What's the final temperature of the H2O sample? All right, let's make some room for this question. Now, in this question, I'm dealing with joules and heat. And if I forget what that problem is all about, I go to table T. Now, I will notice that they're looking for a final temperature, so temperature is changing. So let's go find a place where I can find a formula. That'd be table T. So all our heat or thermal equations that we're dealing with joules are right here. Q equals mc change in T, Q equals m times the heat of fusion, and Q equals mass times of heat of vaporization. Which one do I need? Well, I need the one that has a change in temperature. These are used for phase changes. If you've got solid and liquid, or you've got liquid gas phase changes, you know that there is no change in temperature at a phase change. If you remember your heating and cooling curves, they bottom out at the phase changes, this being a solid, this being a liquid, this being a gas. A solid going to a liquid has a constant temperature because the energy being absorbed kinetically is converted to potential energy. Liquid going to a gas for the same reasons. All right, so we need Q equals mc change in T. They tell you that m is the mass, C is the specific heat, and the change in temperature. What is that specific heat? Let's go to the beginning. Table B gives me the heat capacity is 4.18. So we have our formulas and everything we need now to solve the equation or the problem. Now I'm going to solve this the most simplistic way that I think you could do this. All right, so I'm going to write my formula. Q equals mass of the substance, specific heat of the substance, change in temperature. Now they're looking for the final temperature. So what I'm going to do is I'm going to solve for the change in temperature. If I know the initial temperature is 23, and I know that the water absorbed, right here, the sample of water absorbed that much heat, then you guessed it, the temperature of the H2O is going up. Going up from what? It's going up from 23. If I solve for the change in temperature, you probably guessed it, I'm going to add that to 23. So let's plug the values in that they give me. They give me 209 joules of heat. The mass of the sample is 10.0 grams. The specific heat listed in table B is 4.1, I believe, 8 joules per gram per Kelvin. Now you may say, Kelvins are messing me up because this is in Celsius. Don't worry. A Kelvin degree and a Celsius degree are the same size, so the change in temperature in Kelvin will be the same as a Celsius. Okay? And of course, I'm looking for the change in temperature, which I'm going to solve for. So algebraically, I'm going to solve for change in temperature, and you probably have learned what you're going to do is put these numbers below. So when you rearrange this, change in temperature is equal to 209 joules over 10 times 10.0 grams times 4.18 joules per gram per Kelvin as listed. All right, that's just some algebra, and a quick way to do algebra is if you're going to get rid of these numbers that are not being added or subtracted, you divide that side. Okay, any case, solve for change in t. Now when you do this math, don't do this. Don't do 209 divided by 10 times by that. You're going to have to put these together. I can do 209 divided by parentheses 10 times 4.18, close the parentheses. If you can't do that, then do 10 times 4.18, put that number on the bottom, and then do 209 divided by, because again, if you do 209 divided by this times by that, that will not work. Okay, so I get a change of temperature that is 5, and I'll make it 5.0. Now you may say, Mr. Grodsky, what are the units here? The units are the joules cancel and the grams cancel, and I have the change in temperature in kelvins, but as I notice, that's the same change in degrees Celsius because a degree Celsius and a Kelvin are the same size. So I'm starting with 23. I know my water got warmer. The change in temperature is 5. So all I'm doing here, party people, is adding 23 plus 5, and I get my 28. Okay, now of course, significant figures wise, you should be doing this, and it's 28.0, and the answer is choice 3. Number 41. This is Le Chatelier's question. You have a reaction at equilibrium. I see that it says it's at equilibrium. I also see the double arrow. And what it means is, as fast as silver chloride breaks apart into these ions reform to make the solid. So at equilibrium, the amount of these are staying constant. And what's equal is the rate of the forward equals the rate of the reverse. Now, what's very helpful to understand Le Chatelier's problem is make yourself a chart. We know that if we apply a stress to this reaction, the reaction is going to respond by doing the opposite. So the question states, and the reason why they respond to do the opposite is to regain their balance. So if you're standing over here, okay, this is my great drawing of somebody with some crazy hair, and I push you, you would fall over unless you, what, with your feet, pushed back the opposite way to regain your balance. So if someone pushes you forward, you push back with your feet to regain your balance. Same thing here. We're going to push this reaction at equilibrium. It's going to regain its balance by doing the opposite of what we did. But it's really helpful to see what the stress and the response is. The response is what the reaction does, and the stress is what we, the silly people, do. So when the concentration of Cl is increased, so we're going to increase Cl negative, that's our stress. The response by the reaction to regain its balance is to do the opposite and lower Cl negative. So when the concentration is increased, what happens to the concentration of Ag+? Well, the reaction can only shift one way or the other. Shifting means the forward or the reverse reaction is now going faster. So the reaction wants to lower this Cl because you added too much. So what it will do to lower it to regain its balance, it will shift to the left, as Beyonce would say, I think, and it will use up the Cl and use up the Ag+ to make more of the solid, and it shifts that way, and the response is it lowers it in order to regain its balance. So the concentration of the Ag+ is definitely going to decrease, and the amount of Ag solid is going to increase as the reverse reaction is now faster in this initial shift than the forward, and that's what's going to happen. Now eventually it will regain equilibrium, but this is its first response, just like the first response of the person to regain its balance. 41 is 1. 42, which particle diagram represents a sample of matter that cannot be broken down by chemical means? So it cannot, it's important you read carefully, as I sometimes don't. be broken down by chemical means. Chemical means means breaking what? Breaking bonds. Okay, not just separating. So what cannot be broken down? Well, I'm thinking we got to have some elements. And yeah, I can break this one type of element. If you look at your key here, you have an O, which is atom of a one element, and you have an atom of a different. So to break these apart and separate them, you're going to have to break the bond between them. And the same thing goes for choice 3 and choice 2. But number 4, you do not have different atoms bonded to each other, so you cannot break these down into anything simpler. They're already the simplest form of matter that we count in this course, which is an atom of the same type called an element. You cannot break an element. It's the definition of an element. It's the simplest form of matter. Now, don't fall in love with the fact that you can just break bonds, because if I had two of the same elements bonded, that's a diatomic like H2, it's still an element. Okay, so either it's the same type of atoms singling, hanging out like monatomic ions like helium or any other noble gas, or it's diatomic, hanging out by themselves but bonded to each other. So clearly choice 4 is the only one there that cannot be broken down to anything simpler. It's an element. So 42 is 4. 43, which formula represents an unsaturated hydrocarbon? Unsaturated means there is room to add stuff directly to the carbon chain if you open the double or triple bond between the carbons. This is saturated. This is called an alkane, and table Q will show you that. This is also saturated. Carbon is bonded to 4 things. All right. This is an aldehyde, but still this carbon is bonded to 4 things. Notice these carbons are not bonded to 4 things. This is an alkene. They have less H's because they have to are bonding to themselves in a double bond manner. So in order to keep 4 bonds, because carbon has 4 valence electrons, to double bond or triple bond, you're going to have less H's. Table Q illustrates this fact. Alkanes are single bonds between the carbons, alkenes are double bond, and alkynes are triple bonded. Notice we lose H's as we go. Notice the general formulas are CnH2n plus 2. Then it's 2n, 2n minus 2. We're losing what? As we go from a saturated, which is the alkanes, okay, saturated, I can spell, are the alkanes, as you go into the unsaturated, who have what? Double and triple. There are less H's. This is holding on to the max. That's why these reactions undergo substitution. You have to take one off to put something on. These guys go addition because they've got room if you open up that double bond. So choice 2 is the answer. It's the unsaturated hydrocarbon. Okay, number 44. Number 44. When the pH of a solution is changed from 4 to 3, the hydronium ion concentration of the solution does what? Well, again, hydronium ion, this is the second time in the test they've picked on a hydronium ion. The hydronium ion through table E, if you forget, it lists all the important polyatomic ions. So in table E, you'll see that it is H3O+, which is basically water holding on to an H+ because of its lone pair. So table E will show you that it sounds so very much like the hydroxide ion. This is a markup from a previous question on the same test. So the hydronium is H3O+. H3O+. And how does it become positive? Well, my friends, in chemistry, the H+ that comes off an acid is added to this chain. And this doesn't have any electrons. It's just a proton. So it makes the entire water molecule positive. Hydroxide is different. It's, of course, from bases, or makes up bases that have a metal in front. And this, of course, comes from acids. Now, what you have to understand in this problem is that pH represents the negative log of the H+ or the H3O+ concentration. If it was the negative log of the hydroxide, it'd be something called the POH. So it's about the H plus. Now, I'm not going to get into some crazy amount of math here to explain negative log, but I will tell you it's essentially the positive value of the negative exponent, all right, for your concentration, essentially. Now, if it's changed from 4 to 3, what we mean when a pH is 4, that means the H plus ion concentration, or the H3O plus, okay, oops, as a doohickey, and I will have several of them as I go through this, big fingers, okay, small pen I'm holding. Now, its concentration is equal to 1 times 10 to the negative 4. Notice that's where the pH comes from. What a pH really is the positive value of an exponent, but it's an exponent nonetheless. A pH of 3 means that this same concentration is equal to 1 times 10 to the negative 3. That's a 1. And that's where I get that 3 from. And as you can see, this number here, 1 times 10 to the negative 3, is bigger than 1 times 10 to the negative 4. Now, if you don't see that, let's white this out and make some room. Okay, and it works like this. This is really 0. How many zeros? 1, 2, 3, 1. This one right here is 0.001. This is bigger by what? 10 times. Therefore, the concentration of your H plus ion concentration, your H plus or your H3O plus, increases 10 times. This is really an exponent. Your number's getting smaller as you get more acidic if these guys increase in size, because this negative exponent gets smaller. So as this number gets bigger, let's pretend it gets bigger again, 0.01. That would be a concentration of 1 times 10 to the negative 2, and the pH, if you haven't guessed it, would be a pH of, that's right, 2. So as my pH drops, this number that represents the concentration in molarity gets bigger, but it gets bigger by an exponent, which is a base 10. So 4 to 3 is 10 times. 4 to 2 would not be doubling. It would increase 100 times 4 to 2, because that's a 10 to the what? To the 2. Each change of an exponent in the pH scale is a 10 times change. So 4 to 3 means the acidity, okay, increases 10 times. All right, because we're getting lower, which that means that this number is getting bigger. So you would say that the hydronium ion concentration, which is due to water holding onto protons because of acids, increases by a factor of 10. It would increase by a factor of 100 if the pH went from 4 to 2. Okay? That would be 100, because that means a 10 to the what? 2. Remember, these pH changes are exponents. 44 is choice 2. Number 45. 3 samples of the same solution are tested with each a different indicator. All 3 indicators, bromothymol blue, bromcresol green, and thymol blue, appear blue if the pH of the solution is what? So you would need to go to table M. And they're saying bromothymol blue, bromcresol green, and thymol blue appear blue. So let's go to table M to see what pH would fit in that range. So bromothymol blue went blue. And how to read this is I draw arrows outwards. So that means that everything 7.6 and greater is blue. Bromcresol green, here goes my arrows out. That means anything 5.4 and greater is blue. And then thymol blue is blue when it's 9.6 and greater. So I need something that will make them all blue. Now 9.6 won't make brome-cressyl green. Will make brome-cressyl green what? Blue. All right, because it's above 5.4, and so will bromothymol blue. But we're looking for a choice that is essentially above 5.4 because that's my lowest number. Anything above 5.4, okay, will make brome-cressyl green, but it will not make thymol blue, right? Anything above, so 7.6 and higher would make bromothymol blue, but a 7.6, okay, wouldn't make thymol blue. So I guess the best way I should say this is anything above my 9.6 would make them all blue. Okay, because thymol blue needs at least 9.6. Brome-cressyl green and bromothymol blue need to have at least 7.6 in this case, or 5.4. So it has to be 9.6 and greater for all three. Now, if you notice, for litmus to be red, not part of the question, you have to be 4.5 or what? Less, or thymol blue. Yellow would be 8.0 less, and of course the in-between colors are the ones in between. Yellow and blue would be green. Just some aside fun. So the only one greater than 9.6 that would trigger all of them to be blue would be choice 4. Okay? You can't do it to 5.4 because that wouldn't trigger all of them. So choice 4 is the answer. Number 46, a 10.0 milliliter sample of NaOH is neutralized by 40 milliliters of a 0.5 molar hydrochloric acid. What is the molarity of NaOH? So this is a neutralization problem. And in this problem, we've got 10 milliliters of a base, remember a metal in front with the hydroxides of base, is neutralized by a certain volume and certain amount of acid. Now, when you've done neutralization problems before, you've used this formula, MV, oops, there's my doohickey again, MV of the acid equals MV of the base. So I do, of course, MV of my acid equals MV of the base. All right, now, just going to notice something here, that my acid is monoprotic. There's just what? One H, and my base is monobasic, so it's a 1-to-1. Now, you might see your teacher writing M of A, V of A, M of B, V of B. That's to show the molarity of the base, the volume of the base. And if you forget this formula, table T is your friend. So you see the titration formula, and of course it's a technique where we use information about one chemical to get information about another. Normally we use a standard base, and we know its molarity, which is its concentration. We know how much volume we have to add, usually in a burette, which is an emptying device, not usually bent like that, okay? And we add it to usually a known volume of an acid, and knowing how much volume of base I drop out because I'm matching hydroxides with protons, I keep adding the base until my solution is neutralized, called an endpoint in the titration, sometimes denoted by a light pink color that persists if you're using phenolphthalein, if you did that lab. Now, a titration, as I said, is you're using information about one chemical to answer another. This equal sign is meaning the acid's protons equal the hydroxides, and that's why it works. That's as far as I'm going to go with that. However, what I will say is that some people have a tough time noticing when to use MV equals MV and when to use molarity equals moles of solute over liter of solution, which is also written in table T. And I tell my students, how many values or how many variables do you see here? Here's 1, here's 2, and here's 3. If you got 3 variables, in this case you have what? The 10 milliliter sample of the base. And we have 40 milliliters of the acid. The dot there. And we have a 0.5 molar concentration. That's your molarity. What's the concentration? Now if you notice, I put in the 3 variables, and there's one left over. Now, some people like to write x. I like to write, okay, the, I like to write m of b there. So that tells me what I'm solving for. So m of b. In any case, the idea here is that I have 1, 2, 3, what? Of the variables I solve for the fourth. If you're dealing with this formula, they have to give you at least what? 2 variables to solve for the third. So if you see big M and you see 3 variables, 3 data points that they're giving you, you're going to have this, what I call the motor vehicle formula. Or if you see big M or the word molar or the word molarity and you have 2 variables, you use this formula. One way, but I'll tell you what, 46, put a circle around it. You're going to see this in multiple tests. This pops up either in part 1 or part 2 all the time. So please understand what a titration is, and let's solve for this. So I can probably solve this in my head, not because I'm amazing, because the numbers are easy. 40 times 0.5 becomes 20. Divide by 10, and a molarity is going to be 2 molar, or 2.0 molar, okay? And that's what choice 2 is. All right, and it kind of makes sense when you think about it. We needed only 10 milliliters of a base to what? Match the strength of the, match H hydroxides with protons of the acid. So I needed only 10 milliliters of a base to neutralize 40 milliliters of this acid. So I needed a, what? A fourth as much. So therefore, the molarity or the concentration should be 4 times as strong. If you don't like any of that, just plug it in and solve for it. 2 is your answer. Number 47. Radiation is spontaneously emitted from hydrogen-3 nuclei, but radiation is not spontaneously emitted from hydrogen-1 nuclei or hydrogen-2 nuclei. Which hydrogen nuclei are stable? Stable mean low energy. You've got to get this point down because it pops up in so many different facets of this course. If something is unstable, like an excited state, has high energy, but low energy is stable. And the reason is things that have low energy are going to stay in that state until you give them energy to change. Any case, nuclear chemistry is what these questions are implying about. At the end of each section, part A and B1, you got these nuclear questions, and radiation is not emitted from hydrogen 1 and hydrogen 2 because their nuclei are happy, are stable. If something is changing its nucleus, it's doing so because it has energy and therefore is unstable. So the basis for radiation, the basis for why we give off a beta particle or a positron or an alpha particle is because the nucleus of an atom is unstable. Could be too many neutrons, too less neutrons, too many protons, things that you probably discussed in your nuclear section. So this is a very simple question if you've got this concept down. The reason why things emit particles is because the nuclei is unstable and it wants to change itself into a stable nucleus. When you hear of radioactive decay, it decays into something more stable in its nucleus than it started. So in any case, the stable ones are 1 and 2 only. Hydrogen-3, sometimes called tritium, is radioactive, listed on table N, by the way. So in table N, we find our H3, and this is a radioisotope. And there goes beta decay because of too many neutrons. You don't have to know the neutron part, but this is unstable as everything listed in table N. These are radioisotope, radioactive isotopes of elements. So 47 is choice 1. 48. Number 48, given the equation represent a nuclear reaction, that's important. It's a nuclear reaction. These are the changes not with electrons, but with the nucleus only. So you'll see these with protons and charge designations here. So what is X? Well, thorium by itself naturally transmutates, gets rid of a particle to become stable. And it's getting rid of an alpha particle. And I know that because this is listed in table O. Now the problem wasn't asking for that, but you should be able to identify all these different parts of the same question. However, to answer this question, all you have to do is know that there's something called conservation of mass and charge. What number plus 4 equals 232? Okay, well, 228 plus 4 is 232. And what number plus 2 equals what? 90. Okay, well, that'd be 88. Now, how did I do that? The top numbers, very simply, were added together because of conservation of mass. That's the mass number. Okay, the bottom numbers on each side were equal to each other because of conservation of charge. All right, so I'm looking for element that's atomic number 88 and has a mass of 228. Now, the 228 is not a number I really care about because many elements have many different isotopes, as much as 20. It's very common for elements to have up to 20 different isotopes, which means same proton number, but different number of neutrons. It is this number I need to find the symbol. So I get rid of 1 and 3, and I need to find which element's atomic number 88 to the periodic table I go. So atomic number 88 is radium. Okay, make sure you get the right symbol. So the answer is for 48, 2. That's a 2. All right. What I will say before we move on is that although this was a multiple choice question, you need to be able to do this type of question in part 2. This is a classic part 2 where they may say to you, given thorium-232, draw me the complete nuclear reaction, and you'd have to go to table N to see that it gives off an alpha particle, and they want to see the particle for a point, and they want to see the correct decay product. So that could be a 2-point question. All right, moving forward, number 49. Another nuclear question. After decaying for 48 hours, 1/16 of the original mass of a radioisotope sample remains unchanged. What's the half-life of this radioisotope? Well, this is a half-life problem, and I suggest we do them with a table. All right, now you could do these many different ways. This is the way that I would teach it to, let's get them right. So I draw a 0 timeline. So I have 0 time, if that is 0 half-lives. Okay, and I have 100% of the sample, which I would go 1/1. In the first half-life, we have the first halving, 1/2. In the second half-life, I have a half of a half, which is a quarter. And of course, the third is 1/8. And as I move down, because I didn't plan out properly, the fourth halving is 1/16. So I know that 4 half-lives have transpired. Okay, now the total time they said was 48 hours. So I know that 48 hours has transpired. Well, if the total time is 48 hours and there was 4 halvings, you can do the math to figure out how long each half-life was. And 48 divided by 4 is 12 hours. Choice 3. And if you don't like that, okay, this is the first half-life, 12 days. Another 12 days is what? 24. Another 12 days is 36. And the last one is 48. All right. Any case, choice 3 is your answer. Number 50. Which balanced equation represents nuclear fusion? Okay, well, fusing together means things are coming together. Fission sounds something like it, but nuclear fusion, you just have to identify. First of all, I'm getting rid of choice 2 and choice 4. These are chemical reactions. Why are they chemical? Because they're dealing with the changes of electrons. These are chemical reactions. Okay, these are what we've been dealing with all year long, chemical reactions. Number 1 and number 4 are 1 and 3, I'm sorry. 1 and 3 are nuclear equations where we're showing the changing of the nucleus by either emitting particles or colliding, in this case, with other particles. Now, fusion means that light nuclei come together. Now, you may say, number 3, why can't this be fusing? Atoms are coming together. This represents artificial transmutation. So this is basically colliding and creating this. All right. Now, nuclear fusion, by best, and again, this is a tough one, because you want to see the helium and hydrogen normally, so you may be really tempted to pick number 3. But basically what we take is either heavy hydrogens or hydrogens themselves, and we combine them to make helium. And that change of binding energy from the hydrogen, which pretty much doesn't have any because it has 1 proton, to 2 protons, is huge, and that's what creates a tremendous amount of energy here. Okay, lithium, if you look at it carefully, okay, is being split by a neutron, and this, although it looks like it may be fusing together, this is breaking lithium up into smaller fragments. So this would be something along the line of fission, but I'm not going to even write that because usually you use heavy big nuclei, but we're splitting an atom into smaller pieces here, whereas here we're making an atom become bigger, and 1 is clearly the best choice, and 1 is clearly nuclear fusion. Choice 1 is your answer. And that concludes the multiple choice section. There should be a link at the home screen in the beginning part of this to link you at some point to the part 2.